Hello. So far we have covered the basics for naming ionic molecules and naming covalent molecules. So today we're going to continue on and we're going to move on to actually drawing out those different molecules and what they look like in terms of their molecular geometry. So to really understand how that's going to work, we have to kind of rewind a little bit and we have to go back to electron dot structures. So electron dot structures, if you forgot, is actually drawing out the valence electrons of whatever atom you happen to be dealing with. So to do this, you have to look at your periodic table to figure out what group each atom is in, and then according to that group, they have certain numbers of valence electrons. So, for example, carbon is in group 14, which means it has 4 valence electrons, and you should all have that information down on your periodic table already. Hydrogen is in group 1, so it has 1 valence electron. Bromine is in group 17, so it's going to have, oops, that's a bad 7 valence electrons. So when we're doing the actual dot structure, you have to do the dot drawing in that crisscross pattern that I taught you. You can't just arbitrarily pair up electrons. You have to go top, down, side, side until you run out. So in carbon's case, it doesn't have any paired electrons, just 4 unpaired. Hydrogen's easy with only 1, and bromine is going to have 7. So 1, 2, 3, 4, 5, 6, 7. So what that means is for us, when we start trying to move these things into compounds, the number of unpaired electrons becomes very important. So to just highlight those, all 4 of these are 4 unpaired electrons. Hydrogen has 1 unpaired electron, and bromine only has 1 unpaired electron. So this one here, and all 4 of these are considered unpaired. So just keep that in mind as we keep going. So a Lewis structure is a little different than a plain electron dot structure. What it is it's a combined electron dot structure for every single atom in any particular molecule. And we use them to predict how molecules are going to bond with one another, or how atoms are going to bond with one another to make molecules. In a Lewis structure, a dash is going to represent a bonded pair of electrons. So whenever you see a line rather than just a dot, we're talking about a pair of electrons. And the reason for that is because a dot and a dot are connected by a bond, and then that just makes a line. So I like to think about it like that. You're free to think about it however you want. There are a few different kinds of bonds that can form. We could have a single bond, which represents 1 pair of shared electrons. So for example, in this molecule, chlorine gas, chlorine, by the way, is one of the diatomic elements, so chlorine will bond to chlorine very nicely. So if we were to draw that out, we would draw 2 chlorine atoms, kind of a little bit apart from one another, and then we draw all their electrons. So chlorine is in group 17, so it's going to have 7 valence electrons. So if I just change color real quick, I'm going to draw those in. We go 1, 2, 3, 4, 5, 6, 7. And then over here, this chlorine is going to have the same amount, so we're going to go 1, 2, 3, 4, 5, 6, 7. Okay, now notice something for me. Notice that there is 1 unpaired electron there and 1 unpaired electron here. So the fact that there's 1 unpaired electron in each of these means that those electrons can actually pair up and bond, creating an association between these 2 chlorine atoms. So the electrons do land on the opposite side here, given the way that I drew them out, but that doesn't mean that the bond is going to go like this. That's not what happens. Actually, electrons can move freely around an atom. So in actuality, when you have those two chlorine atoms, those unpaired electrons are just going to migrate around, and they're going to end up in the center, creating that bond. And the other ones are going to, the other pairs that you see, this, they're just going to move around the outside. And so this is what you end up with as the bond between chlorine. You have one line connecting them. And that is what a single bond is. It's one pair of shared electrons. You have the one electron here and the one electron there that are forming that association. Alternatively, you could have a double bond. So let me just show you what that looks like, because a double bond is two pairs of shared electrons. So for that, we have another diatomic element. We have oxygen gas. Again, we're going to draw those two oxygens out, and then we are going to start filling in the electron dots. So oxygen, being in group 16, is going to have 6 valence electrons each. So again, we draw that out. We go 1, 2, 3, 4, 5, 6. And on the other one, 1, 2, 3, 4, 5, 6. So here's what I want you to notice. There's one unpaired here, one unpaired there, one there, and one there. So pretty obviously, these two are going to form a bond because they're right next to each other and then they're unpaired, so they can't. The two on the other side are again going to migrate around to the middle and create a double bond. So when you have your final form of oxygen, here's what it's going to look like. You have that double bond in the middle and those two electron pairs that were non-bonding electrons. So that's here, 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 here. They kind of migrate away from the bond. And this is what oxygen is going to look like. Our third type of bond that could form is a triple bond. Now, a triple bond is thought of as pretty strong, and a triple bond is 3 pairs of electrons that are bonding together. So for that example, we have nitrogen gas, again, another diatomic. So we draw out our 2 ends. Nitrogen is in group 15, therefore it is going to have 5 valence electrons. So we go ahead and we draw out its electrons. We go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So now what you're noticing here is that each of them has 3 non-bonding electrons or non-paired electrons. So each of these 3 electrons can form a bond with another one. So we have 3 opportunities for bonding here. So when you draw out your final form, you end up with a triple bond in the middle, this one to this one, this one to this one, and this one to that one, and they all migrate towards the center. And then these electron pairs that are non-bonding electrons, they migrate out towards the outside. And that's your final Lewis structure for nitrogen gas. All right. So, it's not always the same 2 atoms, though. So here's our sample problem, which is carbon dioxide. The first thing you have to do when you are dealing with carbon dioxide is you have to kind of tell yourself, well, what am I dealing with here? I'm dealing with 1 carbon, that's this one, and I'm dealing with 2 oxygens, and that's those 2. Now, how do I know that it's not going to arrange itself like this? Well, because atoms are generally symmetrical. If there's only one of something, chances are it's going to end up in the middle of the 2 other ones. If it was CH4, chances are the carbon's going to be in the middle and the hydrogens are going to be around it. Atoms just tend to work like that. So this is not what would happen. You'd have your singular atom in the middle of the other two. Okay? So for moving on, I've got my atoms arranged now. So I'm going to go ahead and erase all those drawings, and I'm going to move on to the second part. I'm going to go ahead and I'm going to redraw kind of near the bottom, so hopefully that doesn't impede any of the other text. I'm going to redraw those three. Okay? My second step is to arrange the electrons so that each atom contributes one electron to a single bond between each atom. So that sounds really confusing, but really all that I need you to do is I need you to draw out the electrons of each atom. So for carbon, we're going to see 1, 2, 3, 4 because carbon is in group 14 with 4 valence electrons. Oxygens are going to be in group 16 with 6 valence electrons each. There. So we would draw our 1, 2, 3, 4, 5, 6, and our 1, 2, 3, 4, 5, 6. Okay? So just take a second. I want you to look at these electrons, and I want you to try to take a guess as to what that bonding situation is going to look like. Just try to think for a second. My hope for you is that you paused it and you took a second to think, but really, I want you to know, or I want you to be able to realize that at least there's going to be a single bond between the carbons and the oxygens. You at least know that. Because if it's one molecule, CO2 is one molecule, then everything has to be bonded in there at least once. So hopefully you were able to realize that. Okay, so we have at least one single bond going for us. And then we do this thing and we count the electrons around each atom, and we want to determine if our octets are complete. And again, it sounds really complicated, but it's not. Because all that means is, are all my electrons bonded and paired up? That's what that means. Are my electrons all bonded or paired? And so if we look at this here, they're not, you guys. They're not bonded and paired up, because look how many we have that are not bonded to anything. They're not paired up at all. We have one here, one here, one here, and one here. And what happened all the other times that we had to draw a Lewis structure when the electrons were non-bonded and on the opposite side of the atom? They migrated to the middle and they bonded. So we're going to move them around a little bit. We're going to move those electrons that need to be moved. So this one is going to migrate over towards the center. This one's going to migrate down a little bit. This one's going to migrate up a little bit, and this one's going to migrate toward the center. And they're going to try to bond. Okay? So when that happens, we get another bond forming in here. We get another bond forming down here. But again, that structure looks like really funky. And if you were to write this exact thing on the test, I would be like, I know what you're trying to do, but you did not give me a final structure. So what you need to do then at that point is you need to rewrite it as its final structure, which in this case, I'm going to write it up here. Actually, no, I'm going to write it over here. We're going to have a carbon double bonded to each oxygen, and you have to make sure that you include the leftover electron pairs that did not bond. So in this case, we have 2 on each side, right here, and right there. Okay? So again, final structure is very, very important. And if you didn't already draw dashes in the middle of all of the bonding electrons, you have to make sure to do that. You may not just leave it like this, this is considered incomplete. Do not give me this. That's a no. You have to give me this one as your final structure. And once again, we will do quite a bit of practice with this going forward. I'd also like to talk to you a little bit about resonance structures. And what a resonance structure is, it's more than one possible placement of bonds. So, for example, we have this nitrate here. Nitrate is one of your polyatomic ions. It does have a charge associated with it. And the reason for that is because nitrogen's situation and one of oxygen's situations, they're not full octets. So that charge is coming from the fact that there's a leftover non-bonded electron going on. One of the nitrogens ends up double bonded to an oxygen, but that double bond can move around. And since everything's kind of moving around, that's where resonance structures come from, because atoms are not static. They move around and they shift positions all the time. And so resonance structures are those structures that come from atoms shifting around, okay? I'm not super concerned that you can draw every single resonance structure for every single molecule that we come across. I'm more concerned that you know that they are a thing, okay? Another thing that I need to talk to you about is VESPER theory. VESPER stands for valence shell electron pair repulsion theory, which is, again, annoying to say. So we call it VESPER. Electrons have negative charges, therefore they repel each other. So what VESPER theory does is it takes that into account. It takes into account the fact that electrons repel each other, and it takes into account that molecules are three-dimensional. We're drawing them on two-dimensional paper, but molecules are actually three-dimensional. And so those electrons, those different atoms, will kind of try to be as far apart from each other as they can be surrounding whatever central atom you have. So that sounds, again, super confusing, but it just means what shape is your molecule. Is it laying flat? Is it a straight line? Is it like a weird pyramid shape? Blah, blah, blah. So in class, I'm going to give you this sheet of paper. And I'll explain it more when we get there because there's a way to read this chart. But basically what this does is it summarizes what shape different molecules can have. So let's take a quick look at this linear one because that's probably the easiest to explain. You've already seen a linear molecule. We just drew one together. Carbon dioxide is a linear molecule. It shows up in this shape all of the time. But you can predict when that's going to happen based on how many unbonded electron pairs do certain atoms have? Are there any unbonded electron pairs on your central atom? What's your bonding situation like? How many things are bonded to your central atom, et cetera, et cetera. So pretty much every time you have a central atom with no electron pairs on it, bonded to two other things, you're going to end up with a linear atom. And that's in contrast to this one because there's two things bonded to your central atom, but there's this extra electron pair, and that extra electron pair is pushing everything else into a different shape. It's causing a shift in how those other atoms are located around your central. And again, I know that sounds really complicated, but I will practice this with you in class, okay? But really quickly, I just want to show you this simulation really quickly because it's a lot of fun and I highly recommend that you play around with it. So it's a PhET simulation and I will post the link to it on my Canvas page. But if you click into it, this is what shows up. So we're looking at water right here, H2O. And if you click on different things, if you click on this electron pair right here, or this hydrogen atom right here and you drag it around, you're manipulating that atom. And if I drag it really fast, you'll notice that the atom itself, it kind of bounces around for a little bit and it compensates. Because what's happening when you manipulate this situation is that you're moving the electron pair, you're moving the atom, and all the other electron pairs and the other atoms in that molecule will move around to compensate for that movement. So this is water, which has a bent shape. Here's carbon dioxide, which again, I told you was linear. So you can try to bend it, but that other atom is going to whisk around to that linear shape as fast as it possibly can. Here's CH4 or methane. This has a slightly different shape, so you'll see that that's kind of moving around to compensate for my movement. So once again, I highly recommend that you guys go through this and that you manipulate it yourself so that you can see that 3D shape. And if you click these little boxes down here, it even tells you what shape it's supposed to be according to that chart that was in the notes. Okay? The next thing that I'd like you to do is I'd like you to take a second and I would like for you to practice. I want you to practice drawing these out for yourself. And I'll go over more about the actual shapes of them in class and how you tell and everything like that. But I want you to practice drawing out those Lewis structures. So I'd like for you to pause your notes right here, practice drawing those, and then you can check your answers with what I'm about to do with you. So I went through and I drew out all of these molecules. So my hope for you is that you took my advice, you practiced on your own. I hope that you were able to come up with something similar to what I had for the most part. Maybe your shape was a little off, like you drew it kind of funky, but my hope is that you were able to at least get the right amount of bonds and the right amount of lone pairs that you're seeing. Letter C though, that was a challenge one. So if you struggled with that one, I totally understand why, and I'm going to explain a little bit. So sulfur, based on the rules that I told you, which by the way are not the complete rules in all of chemistry, there's always exceptions, there's always stuff that happens, but based on the rules that I told you, you should have figured out that sulfur and each oxygen all had 6 valence electrons. And so when you were building the structure, you probably figured out, hey, there's not enough non-bonded electrons to contribute to these bonds. So you probably, if you were doing it the way I taught you, ended up with a non-bonding electron on each oxygen. And so what I would like you to do really quickly is go ahead and pull out your polyatomic ion chart. And I would like for you to take a look at sulfate and sulfite. Now these aren't the exact same molecule as this one. SO2 is definitely not sulfate or sulfite. It doesn't have enough oxygens. But take a look at the fact that sulfate has a charge of -2 and so does sulfite. And then look at this molecule and how all the electrons aren't paired up exactly as they're supposed to be. So what that should tell you is that this molecule, like this, is going to have a charge on it. Okay, so I'm going to pause here for now. Your notes document is one document, and there's another part that I have to go over, but that's going to be a separate video. But I would like you to pause. Sorry, that was the bell. I would like you to pause here as well. And I would like you to just take a break before I start talking about polarity and about intermolecular forces. Okay?